Okay, so Newton's third law, it's one of the more poetic laws out there, and it's one that you might have heard or might sound kind of familiar. Newton's third law is that for every action, there is an equal and opposite reaction. So even though in a lot of examples that we draw, or a lot of the examples that we analyze, the problems that we solve, we might only draw one free body diagram, or might just look at sort of one of the forces in an action-reaction force pair, which we'll look at in a second. Every single force in the entire universe obeys Newton's third law. There's not a force that exists that does not abide by Newton's third law, that does not have some equal and opposite reaction. Now, in class, we sort of annotated this, and I'll show this again for our action-reaction force pairs for a few examples. But it's important to keep in mind that both the action and this equal and opposite reaction, those are both forces. So we're not necessarily talking about motion or how an object will move like we did in Newton's first law, and in Newton's second law, we're connecting that to acceleration. Newton's third law is very focused and insular about forces that are exerted. It doesn't really say anything about how those objects will react or anything like that. It's really focused on the forces. So if we look at one example to start off, let's say that we have a fish swimming in water. So if we think about how a fish actually swims forward, and forward, I'm assuming here, means to the right. I guess that's the direction that our fish here is facing. And if we think about this, again, this action-reaction force pair, the action is that the fish exerts a backward force on the water, and then the reaction is that the water then exerts a forward force on the fish. Right? And in class, there were a couple important things that we pointed out as like a general structure for these action-reaction force pairs. So if the action force is about what the fish does to the water, so at first we start out with the fish, the reaction is what the water does to the fish, right? And I should highlight those other things too. So the action force was about what's being done to the water, and the reaction was what the water is doing to the fish. So we've just sort of switched the roles. Who's doing the action and who's sort of like who's receiving that action. And the only other thing I want to point out is something that is hopefully clear from Newton's third law. We've switched the directions of those two forces. So if our action force is a backwards force, the reaction is going to need to be a forwards force. And this is, again, this is a universal structure for these action-reaction force pairs. You could write this, and it would be pretty easy to write these kind of action-reaction force pairs for any force in the universe. The hard thing with Newton's third law is figuring out which force pairs are relevant, or identifying sometimes less visible force pairs than what we see like when a fish is swimming, and it's pretty easy to see a fish pushing backwards on water. So the one thing that we did also practice in class with these is drawing free body diagrams for both of the objects, or for the animal and objects or fluid in the problem. So if we drew that here, let's draw one for the fish. I'm going to leave out masses for now because we're not going to actually solve anything quantitatively with numbers here. We're just focused on sort of what's going on in the situation. So for the fish and the water, draw our fish over here in orange, the water in blue. We'll assume that forwards is like to the right. So on these free body diagrams, we always draw the force that is acting on this object. So if here we're looking at the fish, it would be incorrect of me to draw a force like this towards the water. That would be wrong, because we don't draw what force the fish exerts, not what it does to other things. We draw what's happening to this fish and what forces are being exerted on this fish. So if I want to draw this forwards force being exerted on the fish, I'm going to draw that. And that's kind of, you could call it an applied force because it's something that the fish is sort of purposefully making happen as a result of pushing the water back. We won't worry too much about labeling forces for now. But the important thing that we can do is that we can say that this water, even though it exerts a forwards or rightwards force on the fish, we don't draw that on water's free body diagram. On water's free body diagram, we draw what happens to the water, or what force is being exerted on the water. And one thing that we can say for sure is that these two forces are equal. Now, they don't cancel each other out, though. So the force that's exerted on water cannot cancel out a force exerted on the fish. And an analogy that I used in class was like, when you eat some kind of food, that doesn't fill someone else's stomach, not literally anyway. And when you get money in your bank account on a payday at the end of a long week of working, that doesn't literally immediately put money into someone else's bank account, not without you spending money or donating it somewhere or anything like that. But a force that's exerted on water cannot cancel out a force that's exerted on this fish. So even though these action-reaction force pairs are equal and opposite, they aren't equal and opposite on the same object, because Newton's third law is all about what happens to two different objects, or two people, or people and objects, but it's not just about what happens to one person, one object. It's always about two different interacting things, or two different interacting bodies. So our force pairs never cancel out because they're acting on two different interacting things. Let's look at a couple more examples just as practice illumination of other ways that we can see this. So let's look at an example of a person jumping off of the ground. It could be Michael Jordan dunking. Oh boy, you get to see my pitiful artwork. Okay, Michael Jordan, or any of your favorite basketball players. It could be you. It's definitely not me. Dunking, maybe in my dreams. But if we have this example of the person jumping, right, our action-reaction force pair that allows someone to jump, and it's actually a similar force pair to just someone even walking, is that what we have to do, or what a person has to do here, the action force, is we exert a downward force on the ground, right? When we sort of like flex our legs and we're pushing downwards on the ground. And what pushes us upwards is not us pushing ourselves up. If we were in outer space, we would not literally be able to push ourselves upwards, or if we were in the air and we were falling, we would not be able to push ourselves up. What we need to push us up is the ground exerting an upward force on the person. Right? So if we wanted to draw a free body diagram on this person and on the ground, and I'll just draw a box around the ground, even though that would be hard to do. We'll draw it around this little section of ground that the person is in contact with when they were on the ground. And again, for the ground exerts an upward force. But what I'm going to draw on the ground's free body diagram is the force that it receives, or the force that it is exerted on the ground. So the ground has this downwards force applied to it, and I'll label it this time, although sometimes it does get tricky knowing how to label the types of forces here. And then the person, in return, receives this upwards force. So even though the person exerts a downwards force, we do not draw that downwards force on the person, because we draw the forces that this person receives. It's probably something like a normal force, because this person is jumping off of the ground, off of a stable surface. So I would probably call that a normal force. You maybe could make an argument that that's an applied force, because it's something that the person is purposefully making happen with the action of their legs and the force they exert on the ground. Of course, we know that there would be a gravitational force as well. We don't need to include that always, at least not in just like these examples. If all we want to show is our action and reaction force pair, we could have done that with the water and with the fish as well. Their gravity would definitely act on both of them. There would also be buoyant forces acting there. All I'm trying to show for now is our action-reaction force pair, so I'm going to sort of leave off gravity for now from both of these because I just want to be focused on this Newton's third law force pair. The only other thing that I think would be worth looking at here is an example like a rocket lifting off, because that's one of the biggest misconceptions here, is like when we have something like, oh boy, and here's some more bad artwork. Here's our rocket. We have someone facing upwards, and out of the bottom of this, we can see fire and stuff going out of the bottom of it. It's a very, very crude drawing, but it'll do just fine for us for now. So the action when a rocket is lifting off, or even it's similar to when a helicopter is taking off from the ground, is that controlled explosion and the combustion of the fuel with air. That is, the rocket exerts a downward force on the, I'll say the exhaust, because that's a mixture of not just air, not just fuel, but the combusted materials of those, as well as the water and carbon dioxide that they produce when they're burned. But then the reaction, what really matters here, is that the exhaust then exerts an upward force on the rocket. And one of the biggest misconceptions here is that the rocket must be pushing off the ground. But that's not true, because in that case, if the rocket needed to be on the ground, just like our person jumping had to be, so down here, and I should have put tick marks here, but if the rocket needed to be on the ground in order for this reaction to happen, or this action-reaction force pair to be there, then it wouldn't be able to continue accelerating even after it leaves the ground. But we know, we can see, we can observe and look at NASA videos going back 30, 40 years, that the rocket can continue accelerating even when it's far from the ground, because it only depends on this fuel and this exhaust that it has within itself, and it pushes it one way, and then the exhaust pushes it the opposite way. And that's really the key action-reaction force pair here.